Hello and welcome to the video. Today I'm going to review Rohde & Schwarz FSC6 spectrum analyzer that I have right here, and it measures between 9 kHz and 6 GHz. As you can see, it has a very high portability factor. In fact, you can just take it in one arm quite easily, so it doesn't weigh too much. I would say about maybe 7 kilos. It's also a very budgetary spectrum analyzer in the market. You don't really get the level of quality associated with Rohde & Schwarz for price less than that. Obviously, the main disadvantage of this is the small screen size that can be quite tricky to look at as compared to, let's say, industrial spectrum analyzers that you will see in anechoic chambers there and then. Also, to make this video useful, we're going to look into using this spectrum analyzer to check quality of USB cables. And for those of you who have already seen my how to pass radiated EMC video, you probably already know what to expect from this experiment. Nevertheless, as part of the setup, I'm going to use my near field probes that go between 9 kHz and 5 GHz. So I've got magnetic loop probe and electric field probe. Also, I'm going to use an audio interface to pass the USB signal through the cable, because if you don't have any signal going through the cable, then what's going to create emissions? And that's a very common mistake people sometimes make. They would go to the chamber, connect all the cables, but they will just not click start. And there will not be any applications running on those cables, so there will be no problems. So when you first unbox your Rohde & Schwarz FSC6 spectrum analyzer, it's going to look pretty much like this. So there's not going to be anything external to it. What you do need is obviously an RF cable so that you can connect your magnetic field probes. Obviously, you need magnetic field probes as well, and you may also need to purchase a low noise amplifier. I know it doesn't look like a low noise amplifier. In fact, this looks more like a bit of paperwork, and what it is a unique activation code for the low noise amplifier that is actually already built into the spectrum analyzer. The most ridiculous part about it is that the low noise amplifier is already built into the spectrum analyzer, and you just need to buy this leaflet in order to enable it. And what's the funniest bit of all is that you may have to wait for it. There was actually a 30 days lead time on this paper, whereas the entire time the low noise amplifier was there, but I just couldn't use it. Right, let's enable the low noise amplifier. So in order to do that, you would have to connect your spectrum analyzer to the computer. See how the back of the unit looks like. You have an option to connect it to the LAN. You obviously have a USB port, and you've got various ports that you can use for triggering the spectrum analyzer or generating a difference output, I presume. So now I'm going to insert the number from the back of the analyzer. Now I need to install this file onto the machine itself. So as you can see, I have a very long license key here that I need to type into the device here. Installation successful, and as you can see, I have now got a preamplifier installed on my setup. Let's go back to the screen, and now I suppose I need to actually enable this amplifier. So we've got a few options here, and we want to enable the amplifier that we have just installed. And as you can see, the noise floor dropped immediately, which is a really good sign. So now we are ready to actually connect the cables and start measuring our setup. So the first thing, we're going to insert the RF input here. It is standard 50 ohm impedance, so as you can see I didn't change anything there. You have some limitations here, so the maximum input is 20 dBm, which you have to be careful with, so not to actually break the device, and don't try to insert more than 50 volts DC into this port as well. So this is just some basic common sense that you should follow. On the other end, let's get the audio interface and just try to power it in. This is quite convenient because this is a self-powered audio interface, meaning that I don't need a power supply, I just need to plug in a USB cable. Right, and here you go. The audio interface is actually working, and we can now play some audio into it, you know, whatever. And now you can see that the audio is actually playing. So you can see that the buttons are blinking, which is exactly the indication of its loudness. So that is now working, everything's good, and we can now have a look at the near field setup. So I'm gonna get the other end of the cable. Now that I don't have anything in between, this needs an adapter.
What a twist!
So this is where we're going to end part 1 of this video, because I managed to forget the adapter for the near field probe. I'm back, and I got myself the cable that I managed to forget last time. And this is actually just a simple BNC cable, and basically it plugs in here with a bit of an adapter. And now on the other end we can put the near field magnetic probe. So there you go. And now we can actually start looking at magnetic fields around our USB cables. So let's do exactly that. I have already configured the spectrum analyzer to be in a bandwidth between 100 MHz and 600 MHz. Actually, last time I think it was 200. So let's do that again. So 200 MHz to 600 MHz. And that is so that we can see all the emissions coming from USB signals. The next thing we need to set up is bandwidth, which I see it's already set, but just to go over it again. So by default, the spectrum analyzer will start in automatic bandwidth, and we're looking at resolution bandwidth as well as video bandwidth. So the one we really care about is the resolution bandwidth, because this is what is the eyes of our spectrum analyzer, is the basically the width of its window that it's scanning. So when it's scanning is the resolution of that scan. What I tend to do is I tend to reduce the bandwidth to 100 kilohertz, and as you can see, this automatically also lowered down the noise floor, because it perceives the noise a lot more accurately now as when it was looking with a very wide window at it. With regards to video bandwidth, it's essentially the smoothing effect of the spectrum analyzer. So it's not going to change the peaks, but what's going to happen is that it's going to have different pattern for noise as we either increase or reduce it. So it's a good idea typically to follow it with the same basically value as you set the resolution bandwidth to. So now we can start looking at the actual cable, and basically, if you remember, it sometimes changes based on your orientation. So I'm just going to rotate my probe 90 degrees consistently, and you can actually start seeing that here. So we have a bit of spike, right? And so what we can do to narrow it a bit more down, we can put a marker on it, and basically this is telling us that the spike is around 217.7 megahertz. So another clever thing we can do about this is we can set our trace measurement to max hold. So basically what it means that now, instead of consistently writing and clearing the value of a trace, the spectrum analyzer is going to take its maximum. And this is what we see in this specific area. So what I can do now, I can go throughout the length of the cable, and I will see the maximum amplitude of this signal. So on this spectrum analyzer, when you select a new marker, you have to match out whether it has an M or a D. And basically the difference between them is that D is the delta of the two peaks. So basically what delta tells us is the distance between your M and the spike that you're looking at. So it's a frequency between your first marker and the second position. Whereas your M is your ordinary marker. So what we can do now that we capture this maximum noise coming off this USB cable is that we're going to swap it for a different USB cable and compare. So to do that, let's first capture this trace so that it remains saved in the memory. So I saved some memories, and now I have the memory one that I have enabled on the screen, whereas my trace no longer follows the memory. So I can see that now I can just change that to clear right. And you see that the footprint has been saved on the background. Another way we can do this is by actually selecting a different trace, and to do that you just select a trace 2. So now you can see that on a screen we actually have a choice of traces. We can switch between trace 1 and trace 2. But for the object of this exercise, I'm not going to bother with trace 2. I'm just going to save memories of the same trace. And you can do it with different ways on Spectrum Analyzer. So I swapped it for a different cable, and this time it is connected to the my extension box. And we can see that the audio is playing as it's clearly doing its thing, and we can start looking at the waveform now. So again, we can select the trace mode to max hold, and we can now follow the length of the wire to capture the worst performing area. So you can basically see now that this cable was a little bit worse than the memory I saved of the previous cable. But let's save that as well now and look into another cable, because I have a few more to go to. So now that we've done that, we can export those graphs into R&S Instrument View. So as previously, I will connect to that. And I'm simply going to click Get Trace. And now we can see the traces that we captured on a big screen. So in the measurement setup, it tells us all the parameters that we have selected, be it the center frequency, the span, the reference levels, as well as the range. And most importantly, we have our bandwidth settings, as well as the sweep time. I didn't go over the sweep time too much because most of the time we control it by setting the bandwidth, but essentially the sweep time is the sort of speed at which measurement is taken. I typically have it set to automatic, but you could also adjust it and see how it works for you the best. The trace capture window is not particularly informative, and you usually have to set it up on the spectrum analyzer first. So now let's look through the rest of USB cables that I brought here. So again, let's set the mode to max hold and have a look at the cable. So you can see now that this cable is much better, and it's giving us those kind of very low noise floor that we actually ideally looking for. So now we can get the trace again, and you can see just that the yellow trace, which is our latest cable, has got much lower noise flow at the frequencies between 280 to 400 megahertz, and overall the spikes are much lower, with maybe exception of this particular point here. So anyway, I have now generated 4 plots for different USB traces. Even though I can't combine them within Instrument View together, this is a bit of a limitation of this spectrum analyzer, as it can only plot 2 traces at a time. Still, I can analyze them and draw conclusions based on my observations to select the right cable for my product. And the USB cables are very important because it's your responsibility as a manufacturer to select the right cable that passes EMC. I hope you enjoyed the video. Please like and subscribe, and I'll try to publish more videos about the practical use of equipment for EMC testing really soon.